Dr. Ben Bikman specializes in bioenergetics and researching insulin's role in metabolic disorders and teaching at Brigham Young University. Please welcome Dr. Ben Bikman.
Thank you, Rachel. Thank you so much. Chris, Bear, thanks for the drink at the back. Thanks for representing Utah so well. Chris, in fact, is doing all the video stuff for Dave. It really is a remarkable event. Dave, thanks for inviting me. I am happy to literally be lending my voice in support of this effort. I have long been an advocate of the democratization of science and truly appreciating what the word scientist means, which is as my PhD mentor taught, a scientist is a seeker of truth. And once upon a time, those answers, those truths, were sort of tucked back behind paywalls and written in a jargon that few people could understand. Indeed, you needed a terminal degree, it seemed. But nowadays, it's so much easier to find these answers, and now even easier to contribute to them as well. So I applaud all of the citizen scientists, and I'm delighted to be counted among you. As you know, of course, my focus is insulin resistance. Which is a problem that is getting increasingly some airtime, and rightly so, of course, because this is a problem that is the most common health problem worldwide, and it is so relevant to so many chronic diseases. Now, however, in recent years, I've heard the term insulin resistance invoked improperly, and I like precision. I like words to be used properly and very precisely, just like the razor that crosses my head. I want everything to be exact. In fact, the tragedy of my hairstyle is I actually spend more time doing my hair now than I did when I really was a redhead. True story. Okay, so let's talk about some of the myths and misconceptions associated with insulin resistance. Now, this is the statistic that I was alluding to just a moment ago, where I mentioned that it's the most common health problem. I was amazed with this statistic. Now, just as a point of reference, you'll notice some of the PubMed ID numbers. If you ever have a question about the source, that's your way to find it. I was impressed by this manuscript published a few years ago that indicated that up to 88% of adults within the US were considered metabolically unhealthy. So as the scientists or the clinical team noted, they suggested that it was an alarmingly low number of American adults had a healthy metabolic profile. Now, how did they determine this? Well, they looked at aspects of the metabolic syndrome, this cluster of complications that seems to always come together. And indeed, they do, to some degree or another. And it was that these people, they found that the 88% of adults had at least one of these. And so they were somewhere along this spectrum towards poor metabolic health. Now, earlier, we've heard mention already of Gerald Reaven and George Cahill in particular, and these fellows who contributed so much to our understanding of metabolism also contributed to our understanding of the metabolic syndrome, which again is the absence of these things. And all of these things have something in common, and that's why all of this used to be called the insulin resistance syndrome. I remember when I first found that paper, and my journey into studying insulin resistance is just a remarkable one, and truly, you'll pardon me perhaps if this is offensive, I thank God that I was directed to study what I do, because it's something that I love talking about, and it's something that matters, and I indeed have felt somewhat directed in my life. So let's talk a little, thank you. Let's talk a little bit about insulin resistance then. In the past, as you have heard me talk about this before, if you have ever heard me, maybe some of you haven't. I'm Ben, nice to meet you. But I've always talked about the pathological side of insulin resistance, the version of insulin resistance that is contributing to all of these chronic diseases. And none of these is put here by happenstance. Again, very precise. There's evidence to support insulin resistance being causal or an exacerbating factor in every one of these disorders. And this is, which is one of the reasons why I beat that drum so loudly. If you became aware that amongst all the medications you're taking for your variety of chronic diseases, that there was one single thing you could do, one strategy you could embrace to improve one particular outcome, and in so doing, reduce the risk or improve the outcomes associated with all those diseases, wouldn't you want to know? I think you would. So this is the pathological version of insulin resistance. However, there is a twin. Like Dr. Johnson's tale of two sugars, there's a tale of two insulin resistances. There's a pathological version, and there is, in fact, a physiological version. Some of you have heard this term before, which is the point of this talk, because if you have heard the term physiological insulin resistance mentioned in any context other than growth, you've not heard it mentioned properly, because this is when it is relevant. Now, the pathological version of insulin resistance is an insulin resistance that hurts your body and contributes to diseases, as indicated. Whereas physiological insulin resistance is one that develops at a particular time of life for a particular purpose. It serves its purpose and then it goes away. Now, over the time we have together, and I'm particularly delighted that I was given a little more than some others because it's hard to get a professor to stop once he gets going. So don't try to stop me. I got my eye on the clock and I'll make sure I do it in time. But I would love to have time for questions at the end, so I'm going to keep a pretty good pace. So over the time we have together, I want to go through 3 questions, making sure that we have a common definition of insulin resistance, understanding the origins in both pathological and physiological, and then touching and answering explicitly the question that gave rise to physiological insulin resistance being invoked improperly, which is, what is the relevance of insulin resistance in the context of a low-carbohydrate diet? Because that's where there is a lot of misunderstanding. Okay, what is insulin resistance? Let's start by just noting insulin is unique among its class of hormones because it is capable of affecting every single cell of the body. And that is rare among a lot of hormones, and there are so many different types and so many different families. But insulin stands apart because every single cell of the body, from brain cells to bone cells, from lung cells to liver cells, has insulin receptors, little doorways that are specifically designed for insulin as it is flowing through the blood to come and knock on the door of the cell. In so doing, telling the cell to do something. Now, that something can depend on the cell, which is why I'm giving it this very generic title of action. Because what insulin will tell an erythrocyte or a red blood cell to do is very different from what it would tell the theca cells of the ovary to do. And so we'll just call it action. Now, unfortunately, and its most famous action is its effect on glucose. Where, and again, I emphasize my word here, my wording, which is its most famous. What I'm not saying is insulin's most important action, and indeed, so many people view glucose regulation as insulin's most important action that they get into trouble. They don't understand insulin resistance properly and are left focusing on a marker that doesn't matter as much as they think, namely glucose. Now, nevertheless, insulin's most famous effect is to knock on the door of some cells and open the door for glucose to come in, to be stored or to be used for fuel, or to be turned into fructose or something else. It's somehow going to be metabolized. So that's its most famous effect. Now, unfortunately, due to certain stimuli, which we'll get to in just a moment, and I'll highlight what I consider to be the primary ones, the action of insulin is going to be reduced. And so this right here is the insulin resistance part of what we call insulin resistance. And so the most famous and long-awaited consequence of this will be that glucose levels start to climb. Now, as glucose levels start to climb, it actually ends up contributing further to this vicious cycle, where if this much insulin is insufficient to keep the glucose where the body wants it kept, well, then the body can respond to that and increase the amount of insulin. So now what was once a polite knocking on the door of the cell becomes an angry mob, all in an effort to try to get the cell to listen as well as it did before and restore its action, which to varying degrees is capable of working. But right now, there's a very important thing to note, which is that insulin resistance, or a cell not responding, is not a universal phenomenon. That only happens at some cells of the body, whereas other cells of the body are as insulin sensitive as they ever were. But now they are subjected to the angry mobs and they answer to all of it. And so whereas one cell has a reduced sensitivity to the signal, another cell, because of all of the insulin now, is over-responding. Indeed, that brings me to the next point that I've been alluding to. So there's really two aspects. So insulin resistance is a coin with two sides. One side being that insulin isn't working properly at all of the cells of the body, certain cells of the body. And two, is that when we zoom out from the cell and look at the whole body, insulin levels are much higher than they used to be. And this is so important. There is no insulin resistance without hyperinsulinemia, unless a person is truly starving, like true starvation. That's a little asterisk. True starvation actually can cause insulin resistance without high insulin. Anything other than true starvation, like you've run out of fat and now you're burning muscle for energy, is going to be this. Insulin isn't working particularly well and blood insulin levels are higher. All right, so that's the definition. Now let's actually get into the question that I teed up a moment ago, which is where does it come from? You've seen, likely, if you've heard me or seen me present before, I use this paradigm a lot, and I'll find a new way to present it, lest I start to bore you, because nothing worse for a professor than losing his group of students because they get bored. So here we have the typical timeline. In fact, let me back up for just a moment. The primary clinical marker of insulin resistance is glucose, and that is because a conventionally trained clinician has a hard time separating the two. Or I have had amusingly, frustratingly circular discussions with clinical groups where I will say, in order to understand insulin resistance, you must measure the insulin. And they will say, well, I don't need to measure the insulin because I'm measuring the glucose. And I will say, no, to measure insulin resistance, you need to measure insulin. No, I don't need to measure the insulin because I'm measuring the glucose. It literally just becomes circular. But we just have to remember that they are not the same thing. And as much as glucose is the primary driver for insulin, I will use the definite article there, high glucose is the main driver of insulin. It does not mean that they're always going to be coupled. And indeed, in insulin resistance, most especially at the front end of it, you'll notice that it's not. And indeed, let me just really bring your attention to that by superimposing two distinct time points. The first being a state where glucose is persistently staying in a normal range. Even if it is slightly elevated, perhaps it's not reached a point of problem by conventional clinical metrics. But while the glucose is staying normal, the insulin is not. It's taking ever more insulin to keep the glucose in check. In other words, the insulin isn't working particularly well at these tissues. And I'll emphasize those tissues more in just a moment. And then eventually, due to a handful of stimuli, the person would start to have this inflection point, and now the glucose starts to be elevated. But if it is true, and then they've ventured from prediabetes, which is synonymous with insulin resistance, into full type 2 diabetes. And at that point, it's important to note, no surprise, there's no accident. If it's true type 2 diabetes, insulin will never go to zero. If that's happened, it's no longer type 2. It is, as Jessica discussed earlier, it is LADA, L-A-D-A, which to me is a cheap Soviet-era vehicle, having lived in Russia, but it also means something else. Okay, that's a pretty obscure reference. Does anybody get that reference? Yeah. Okay, so here we have the insulin curve. If you compare the type 2 diabetic, even if insulin has come down, it is still multiples higher than where it was when they were insulin sensitive. This is exactly what it's going to be like. If anything, it just as often can stay up here and it would have been a hashed flat line. Insulin does not go to zero, even if its production has started to come down, which would certainly accelerate the climbing of glucose. Okay, but if we're looking at insulin resistance, we need to appreciate the insulin curve. Now, let's superimpose even another layer here and talk about the tissue origins. Even though I'm not going to revisit this, this would be a topic for another time, and indeed, it has been a topic at other times for me. I firmly have a fat-first focus when it comes to the order of tissues that become insulin resistant. I very much believe that it is the fat cells that become insulin resistant first, and then they begin to heavily contribute. It's the first domino, if you will, that tumbles into the other dominoes, these tissues that when they become insulin resistant, actually I can go ahead. When they become insulin resistant, that's when the body has a very hard time controlling the glucose, which is why I put it where I did. So I'm putting that the fat cells are really the first thing that's starting to move the body into this realm, and then as these tissues become insulin resistant, now we start to have that uncontrolled glycemia. Okay, now there can be some variety to this, but I very much espouse this progression from tissue to tissue. All right, now here are what I consider to be the primary causes of insulin resistance, but I am acutely aware and even deeply appreciative of the fact that just in today's lectures, we've heard mention of two other causes, including uric acid, and including the permeability of the intestinal wall being leaky. I very much actually appreciate both of those and agree with them. It just seems more and more that those work primarily through inflammation. So I have what I consider to be primary causes that each one on its own is capable of causing insulin resistance, and these are just a handful of the citations. I've put more on the hyperinsulinemia just because there are so many knuckleheads who rail against that fact. And I've literally done those experiments with my own hands, and so I feel a particular, indeed some of these citations are mine, so I feel like it's turf that I'm prepared to defend quite vigorously because most of the knuckleheads have contributed to none of this work. They just speak with a false authority. So, yes. All right. Now, let's just go through them very, very briefly. And it's my particular delight right now to mention some of these things because right now, as a professor, I'm teaching a graduate level in endocrinology. And we've just got done actually going through adrenal gland endocrinology, so looking at the adrenal glands and its contribution, which is heavy and substantial. The adrenal glands, among the myriad hormones they produce, have these two famous stress hormones. Indeed, these are the poster children of stress hormones. There are more. But what's interesting is that while we call them both stress hormones, they are totally unrelated. They come from different cell types. They come from two parts of the adrenal gland that may as well not even be part of the same gland. They're so different. They come from different cell types. They're produced from different kind of origins. They're different types of hormones. They move through the blood differently. They act on different tissues differently. The one thing they really appear to have in common is that they both will increase blood glucose. Whether it is very rapid or a little slower, they both want to push glucose up. Well, that puts them at odds with one particular hormone. Can you think of what it might be? Yeah, of course, there's the humble hormone insulin that now has to work a lot harder. So let's feel a little sympathetic for it, but suffice it to say, if these two signals are persistent, that means the upward pressure on glucose is persistent, and that simply means insulin has to work harder and harder, and we would call that insulin resistance. All right, now inflammation is one that I also enjoy talking about. I don't teach a class on it. That's actually more the realm of my colleague who's here, Paul Reynolds. In fact, if you haven't, please go find him on social media because his contribution to the field more and more is looking at glycation and inflammation. And suffice it to say, when cytokines are elevated, cytokines being these sort of, if you will, hormones of the immune system, they will promote a reduction in insulin sensitivity, or they will promote insulin resistance. And you see this anytime there is this upward pressure on inflammation. Something like the hypertrophy of the adipose tissue, or as Paul Reynolds and I have already published, a couple of these are our papers, diesel exhaust particles and cigarette smoke. We've published reports finding that they cause insulin resistance, and autoimmune disorders do as well. In fact, Paul and I are just about to publish a paper finding that diesel exhaust is capable of forcing adipocyte hypertrophy, even in totally independent of any calorie signal. Eat the same amount of food, the animals get a little scrawnier, but their fat cells get fatter. And that is not a good trade-off. They're eating the exact same diet as their they're identical twins. And just the exposure to diesel exhaust being inhaled was actually causing this adipocyte hypertrophy. Okay, now the last one I leave deliberately at the end so that I can emphasize it a little more elaborately, and that is that too much insulin will cause insulin resistance. Again, this is a principle that people rail against, and you can just laugh heartily and make them all the more frustrated as you do so. A tactic that I always encourage my kids to do in order to try to mitigate the fighting. Just laugh at them, I say. Laugh at your sibling, and it'll make them even angrier. Just to try to diffuse the tension, and it has not worked yet. But I'm gonna keep saying it. All right, now, but even this is reflective of a fundamental biological principle, which is too much of something will cause a resistance to that something. We see this manifested just throughout all of nature, throughout all of biology. The reason individual chemotherapeutics aren't used, it's always a gangbuster version of a chemotherapeutic. Why one antibiotic has to be rotated out, or you can't keep taking it. Whether it is caffeine, whether it is other hormones, if there's too much of a signal, a cell will attempt to become resistant to that signal in order to maintain its homeostasis. And in particular, although I'm not going to revisit this because it is a whole other topic, as insulin is elevated, it will directly promote adipocyte hypertrophy. This is an effect that is so relevant that there are studies in humans to look at in insulin-treated diabetics. That would include type 1 and 2, although type 2 should never be treated with insulin by my understanding. But you can take an area where they've been giving themselves their insulin injections, take a fat biopsy right here, and then take a fat biopsy right a few centimeters to the side of it. And these fat cells that are getting the insulin injections are multiple times larger in volume. And it's just because of all the insulin. So anyone who tries to tell you that insulin's not promoting adipocyte hypertrophy, join me once again in laughing in their face and enjoying their frustration growing even more. You can tell that I'm one of 13 kids. And I'm the youngest brother, so I have very mature tactics on irritating siblings. And it appears, as I think about this in real time, that it's a metaphor that I go to often, even though I don't intend to. Okay. So here we have the pathological, or the pathogenic version of insulin resistance. These are the pathogenic contributors listed here. I consider them to be the primary causes because they're each independent of anything else, but then I would have a different list of secondary causes, which are very much relevant, including the ones I mentioned earlier, and even a few more. So if you're looking at this and you are indignant that I've left something off, I'm probably familiar with it. I just have my own sort of internal classification, and because you're here listening to me, I get to be the one who says what I want to say. All right, now, what about the physiological side? It is a different beast. It is a different version of this disorder. And what contributes to it? What is its unique etiology? Well, it is not as unique as you'd think, because one of these is also relevant to the other side. So hyperinsulinemia, just as much as it is a cause and consequence of pathological insulin resistance, it is also cause and consequence with physiological insulin resistance. So we need to appreciate that it has this sort of dual role here. But also we have a new character that you've never heard me talk about, which is growth hormone. Growth hormone is another endocrine contributor to physiological insulin resistance, and in fact it is the main one. Growth hormone is, I would say, fundamentally misunderstood. When you think of growth hormone, just humor me as the professor for a moment, what do you think its primary action is in the body? Growth. And as your professor, you would have gotten the question wrong. Growth hormone, its actual primary responsibility is to fuel the growth. Most growth actually happens from downstream products of growth hormone, a family of hormones called the somatomedins, which are the insulin-like growth factors. Have you guys heard of IGF-1 or 2 or 3? Those promote growth. Growth hormone primarily fuels that growth. And one of the ways in which it fuels, it mobilizes the energy to fuel the signal of growth. And one primary fuel that gets mobilized is blood glucose. So growth hormone will increase blood glucose substantially. And any disorder of excessive growth hormone, like acromegaly. For example, if some of you have heard of that, it's almost a guarantee that person's going to become type 2 diabetic. They become so insulin resistant because of this constant, incessant pressure pushing up the glucose. And as you saw earlier in a very similar paradigm, if glucose is constantly being pushed up, who has to work a little harder to push it down? Yeah, of course, insulin. So it's no surprise that as growth hormone is a persistent signal, that the body becomes more and more insulin resistant. I kind of did a lot of pull-ups today, so this mic is getting kind of heavy. Dr. Johnson always wants to know how many pull-ups I do. I think Rick, every time we talk about workouts, he's like, how many can you do, Ben? He's like sizing me up. So Rick, someday you and I are going to have that competition. Okay. And we'll do it with our shirts on, I'm afraid, everyone. So Rick and I have very strict no nudity clauses in our social media. Okay. All right. So hyperinsulinemia and growth hormone, when are they relevant? Well, it is the 2 P's of physiological insulin resistance, namely puberty and pregnancy. What on earth do these 2 states within the life of a human, within the life of all humans that get to adulthood and some humans, who are fortunate enough to contribute to the human race in a meaningful way, and I do really, truly mean that, exclamation mark. Puberty and pregnancy, they are both, what they have in common is that they're both times of explosive growth. Truly the most remarkable condensed growth is going to happen during these 2 times. Any other time of growth is going to be a little more subtle, even though childhood and infancy is pretty quick. It pales in comparison to the growth that happens during puberty and even during pregnancy, where mom's body is changing substantially, and also she is very, very busily growing the next generation. So let's start with puberty, because puberty would come first. You'll notice this is a little tricky because I have 2 y-axes, so pardon a little potential for confusion. But as usual, don't underestimate my color coding, where insulin resistance is this dark blue and insulin itself is this lighter royal blue. That's not quite royal, but a lighter blue. So this is what insulin levels would look like through the life of an average individual. As they go from infancy, it's climbing a little bit, and then boy, when they get towards the end of childhood through adolescence, insulin levels go up substantially. I'm being a little dramatic here. This is not actually tracking a real figure, so pardon me being a little dramatic. But then at the end, it starts to go up as most people start to become more insulin resistant with age for reasons we won't get into. But if we have time for Q&A, I'm happy to explore it. Now, if we superimpose insulin resistance, boy, it looks remarkably similar because they always go together. So if insulin resistance is up, no surprise that we see that the insulin levels are tracking. Now, I mentioned another hormone a moment ago, and just before we mention that, let me just show you, type 1 diabetes is just such an easy way to show the dynamics of insulin resistance. And you can see over the life of a person with type 1 diabetes, this peak during adolescence, that they need more and more and more and more insulin per kilogram, so it's being controlled for body weight. And then even as they continue to get older and bigger and older and bigger, you can see that the actual amount of insulin they need is dropping. This is a perfect example or a perfect display of what insulin resistance, how insulin resistance is changing during the age of the person. Now, let's bring in the other variable that I mentioned a moment ago, and growth hormone is going to follow a similar trend. Growth hormone is generally fairly low, and then it really climbs during adolescence and starts to come back down and continues indeed to come down somewhat through life. All right, now let's go to the next one. With pregnancy, the second P of the 2 Ps of physiological insulin resistance. The insulin resistance during pregnancy is largely the result of this new, very active endocrine tissue, the placenta. And it is a very active endocrine gland. It produces many, many hormones that are spilling into the body of the mother, and then contributing very much to the development of the baby. And among the many, many hormones, there are a couple worth mentioning. Human chorionic somatomamotropin, and then human chorionic gonadotropin, HCG, which does contribute to a sense of nausea, which is generally why it was used for weight loss, because it makes you a little sick, not unlike GLP-1 agonists. And then human placental growth hormone. That's the relevant one in this story, because human placental growth hormone actually becomes the main source, and it's not even close, of growth hormone in mom's body. So when that placenta starts producing growth hormone, it almost completely replaces the growth hormone coming from her own pituitary gland. The pituitary gland basically says, all right, I can take a back seat, because all of the growth hormone starts coming from the placenta, and it is more than before. It goes up a lot. And so this now is the same version of what we saw with puberty, but here we see it with pregnancy, where instead of adolescence, we now have pregnancy itself. And this is a very natural, remember, this is physiological. I would hate for any of the ladies here to think, oh man, it sure sucks to be a woman because I'm going to get insulin resistant if I want to reproduce for the good of the species. No, don't curse it. You need to have it happen. It is natural. Even the healthiest pregnancies will manifest with an insulin resistance. But just to show you how relevant this is, look at the insulin demands required. This is, in fact, superimposed. I literally just did my own version of the graph because I hated the way it looked. I have a particular aesthetic, which I know is funny for a bald, shriveled, freckled guy to really care about how things look. You think I'd be a little indifferent about it, but I actually am not. I have a very particular style, so I just superimposed a figure on one that came from this paper. But look at how much the insulin changes. Over the course of the pregnancy, the amount of insulin the woman has to treat herself with doubles. And this is, again, even looking at changes in body mass, the needs go up substantially. So when we look at the human placental growth hormone curve, no surprise that it's following a particularly similar trend. And this is why during the course of the pregnancy, she's going to be getting ever more insulin resistant until the time that the baby is delivered. Now, one other comment with regards to the placenta, not only do we have the placental growth hormone, which is compromising insulin sensitivity in the mother, but then we have a variety of cytokines that are produced. And you'll recall that I just mentioned the cytokines when I talked about inflammation. Now, why is her placenta producing cytokines? It's actually the same reason why the hypertrophic fat cells produce cytokines, which is to stimulate vascular growth. This is a way to basically, in addition to activating immune pathways, one of the upsides of these cytokines is that it's stimulating the growth of new blood vessels, which of course you need enormously, if nowhere else than for the sake of the placenta, which is growing substantially. Okay, now let's get to the last point that I'll make in the minutes that we have left, which is the degree to which a carbohydrate-restricted diet is capable of causing insulin resistance. Is it even capable? The answer is a resounding no. So anytime you hear someone state, and very prominent voices on social media will state, that a ketogenic diet causes physiological insulin resistance, and they preen because they think they sound so clever, it is not true. It does not cause insulin resistance. You don't meet any of those. I mean, even if someone says, well, I'm cutting carbs or I'm fasting, so I have a little elevation in growth hormone. You have a modest elevation in growth hormone, but at the same time, your insulin has bottomed out. You can't find a person who adopts a ketogenic diet and their insulin levels go up. It is antithetical to the very process of ketogenesis. Insulin will always come down, and so you're immediately stripping away one of the absolute essential variables that is a feature and a cause of physiological insulin resistance. So while the answer is a resounding no to the question, does carbohydrate restriction cause physiological insulin resistance? However, there's a but. No, but insulin production changes from the beta cells. And now we're really getting to the meat of the matter here. So if insulin production changes, it's not surprising that you can expect to see differences in glucose dynamics in certain instances. And this is the instance I mean. So if someone does an oral glucose tolerance test, a normal person who's eating a standard Western diet, which is to say it's abundant in carbohydrates, but they have managed to stay insulin sensitive, which some people do, either due to age or athletics or whatever, but they eat carbs. Their body is accustomed to using carbs for fuel, and they're insulin sensitive. Now you'll notice the insulin is going to be the hashed line and the glucose curve is going to be a solid line. The glucose line will look something like this. So it's come up to a nice degree, and you'll notice I'm not putting any metrics here. That's for no particular reason, what the actual glucose would be. But it's important to note that it reaches a particular height and then it gets back close to fasting by around, close to its original stage by around 2 hours with this given load of glucose. Then the insulin curve, and this is what is really important to the topic at hand, you'll notice that it has a unique shape to it, where the insulin curve has 2 phases. Insulin has a first phase and a second phase in response to a carbohydrate load. And this is all about what is in the beta cell at the moment the glucose hits the system versus what the beta cell makes next. So the first phase is a result, as blood glucose goes up, of the initial, or the insulin that is already on hand. So the beta cells have some shelves filled with insulin that are ready to be shipped in the moment the glucose comes in. It activates a series of events. The beta cell is ready to go. They say, I know what to do here. I already got this insulin ready to go. And it dumps out that little bit of insulin that it had pre-packaged. But then it continues to sample the blood. The beta cell acting as a bit of a thermostat. It's sensing the change, the environment. And it realizes, okay, this little bit wasn't enough. So let's start ramping up production. And now we start turning on all the machinery to start producing new insulin from scratch. And that is the second phase, which is a little longer and it's a little more fine-tuning, all in an effort to make sure that we get that glucose level back under control. Now, if we take this normal diet, insulin sensitive, so eating carbs but insulin sensitive, and then view it with a new set of curves, we then can introduce the normal diet but insulin resistant group. And in this case, they're both going to be elevated. In fact, if anything, my glucose curve's a little too low. I should have put that one up a little higher. But at the very least, it won't drop down to even near normal by the 2-hour point. And this is a separate phenomenon than what we see happening with the insulin, which is still 2 phases, but much, much higher. Again, if anything, it would be even higher than how I'm indicating it, how I'm showing it here. So in this case, the person is insulin resistant, which is reflected in the higher insulin levels, and they are glucose intolerant. The glucose, it's taking the body longer to clear the glucose. I gotta speed up. All right, now what if a person is insulin sensitive and they're on a ketogenic diet? Now in this case, the glucose level will actually be more similar to the glucose curve that you saw in the insulin resistant person. So that if you only looked at glucose, what would you think? You'd think, well, this person's insulin resistant because that's a pattern that we see in someone with insulin resistance. And yet, if you look at the insulin, it is a completely different curve, unlike anyone you'd seen before, which is, what's different about this? There's no first phase, and let's just get to that for the sake of time. So here, the beta cell is so efficient that it looks at all of the insulin that it has pre-made, that is ready to go, and it starts to think, mind you, much more quickly than you would imagine, and I'll touch on this in just a moment. It starts to think, I don't need all this insulin cluttering up the place. It's basically me in my home, where I throw anything out. It has been a source of constant marital strife. And I just live in constant fear, thinking, like, I can't help myself to throw something away, and I think, oh, is Cheryl going to ask for this? Oh my, please don't ever ask for it. And boy, have I got some stories. But I keep a very tidy home, ladies. It's all me. All right, so the beta cells are looking at all the insulin and thinking, I don't need all this insulin around here. It's just cluttering up the place. We're not using it. Let's just get rid of it. And so it literally breaks it down back into its component parts. And so there's no first phase. As you noted, the first phase is gone. There's just not enough there on hand. And so everything is crank up the machinery, red alert. We actually do have glucose coming in. Sorry, guys, I let you all go home from the insulin-producing plant. I need everyone to come back in immediately. We got to start making insulin. And thankfully, the beta cells are still there. The beta cells are more than capable of producing insulin. They just didn't know they needed to. But they get the job done. Ultimately, it just took a little longer than expected. So the loss of the first phase and a somewhat delayed second phase ends up contributing to a much higher than normal glucose curve, causing glucose intolerance, even though they're insulin sensitive. And I have done these experiments in my lab with animals. George Cahill has done similar experiments in humans. But if you take a ketogenic diet adhering animal or human and put them on give them a spike of insulin, it's no surprise to see that they are so insulin sensitive that in some instances you actually have to intervene, because one bolus of insulin will work so well that you have to almost rescue and give them some glucose. But that is itself a reflection of a body that is very insulin sensitive. So this is, and mind you, it doesn't even take a ketogenic diet to see this effect. Even if you fast, we have known within the clinical realm for years that if a person fasts too long, they'll get a false positive. They'll fail their glucose tolerance test because the beta cells are so efficient that even after 12-ish hours, you've started to lose some of your on-hand insulin. Your first phase is going to be compromised. So if you have to go in and do a glucose tolerance test, you need to kind of play the system, which I'll get to in just a sec. Now, I've actually was asked earlier about the Randle cycle. We've heard it mentioned here. This is, if you will, the most succinct version of the Randle cycle, which is that the cell only really wants to burn primarily one fuel at a time. It can't be burning all the fuels at all the time. Well, I mean, it can, but to varying degrees. But it's insulin that determines generally which fuel is being used. So if insulin is up, the cell is burning glucose. It is sugar burning. In contrast, if insulin is down, the cell is fat burning if it has the potential, which is pretty much everything but the red blood cells. This is metabolic flexibility, the ability to move between the two primary fuels. There are other fuels, but these are the main ones. Now, metabolic inflexibility was a term first invoked by scientists at the University of Pittsburgh, and they noted that even when people were fasted and they should have a low insulin level, that they were still burning glucose. Now, I sort of swapped the animations. I should have had the carb burning go first and then the high insulin, but these are people who are insulin resistant. If insulin is persistently high, the body will have a hard time moving back to fat burning because it's insulin that's dictating which fuel of the two primary fuels is the one that's actually being burned. Now, then, with that in mind, let me just introduce to you a different idea, which is this concept of reverse metabolic flexibility. My own term, and I'm sure we could have thought of a better one collectively, but this is the state of a low-carb diet. This is someone who has been eating so few carbohydrates that their insulin production is almost now chronically low. And thus, it's almost as if they are stuck in fat-burning mode. Just like true metabolic inflexibility is the person being stuck in sugar-burning mode. This is the exact opposite. And so if the body is somewhat stuck in fat-burning mode, if you load the system with some glucose, it's no surprise that it's going to have a bit of a hard time switching right over to glucose because it's not accustomed to it. It still can, but if you load the system with glucose, don't be surprised that it takes a little longer to clear it when the body's been primarily relying and indeed has adapted to burning fat. This is what you get with a low-carb diet. So if you are on a low-carb diet and you don't want to fail the oral glucose tolerance test, you simply understand the demands of the pancreas and the beta cells, and you say, I know my beta cells aren't going to have a first phase of insulin secretion, so I'm going to remind them how to do it, which is going to be simply eating some carbs a few hours before the test. Truly, if a person does this, they will take what would have been a fail and they will pass it with flying colors. It will work every time, and then you leave with a pat on the back. And your clinician never needs to know that you're actually adhering to a diet that's going to kill you. Okay, so thank you. This is what we've covered. You are now experts on answering these three questions. What is insulin resistance? Where does it come from? And how relevant is it in the context of a ketogenic diet? I hope you feel like you have learned. And we do have a little time for questions, a minute and a half. So I would love to get some if you got them really quick. Yeah. Yeah, Beard, go. Clots in your blood? Well, I don't know. That's a good question. I've never heard that before. Insulin does have an effect on thrombogenesis and the clotting factors, but which isn't to say that it's an inherent evil, but the degree to which exogenous insulin is going to influence, I don't know. Yeah, I'm sorry. I think one of the clinicians may know a little better. I'd say somewhere in the order of a few dozen carbs. If you're getting up to around 50 to 60 carbs within that handful of hours. There was a paper that was just published about 2 years ago talking about how with the rise of focusing on HbA1c, clinicians have forgotten how to do a proper oral glucose tolerance test, namely encouraging the person not to fast too long. Yes, let's go to someone at the back. Yeah, right there in the middle. What happens if the child is insulin sensitive when they enter? Is not? If they're insulin resistant when they become adolescent? Yeah. Yeah, well, one of two things can happen, and it's primarily going to be a function of what they're eating. They're either going to become insulin no, they will become more insulin resistant. But then it's how they come out of it, I would say, is the bigger question. You cannot avoid being insulin resistant during adolescence. Whether it gets a little worse, that would be unknown for me. But the question is, how do you come out? Because if you were insulin resistant before you started, it's possible you'll stay insulin resistant when you come out, which is important because the number of fat cells that child lays down during puberty is going to be the number they basically have for the next 40 years. So puberty, when my kids have gone through puberty, one already done, one going through it now, one about to in a couple years, I am extraordinarily mindful of what we're feeding them at home. Never judgmental, never mean, never overly authoritative, but we're the parents, we decide what comes into the house. We can't decide what they eat outside the house, but when my kids start to go through puberty, I'm incredibly mindful of we helping them create the body that they're going to have, for better or worse, or the body that they're going to want to have, and they're going to have to fight it or enjoy it throughout all of adulthood.
Professor, one more very important question.
Hey, Ken? Yeah.
Is it possible for someone to eat low carb, too low, too long, and develop some sort of pathological insulin suppression?
I know of no evidence that suggests that the case, where we have animals, for example, that have been on a ketogenic diet essentially their entire lives, what would be the equivalent to 50 years of a human lifespan. And this is rats, and rats are substantially more metabolically accurate as a human model, and there's no evidence whatsoever. They are immediately able to just go back to burning carbs, and you give them a load of insulin, and boy, it will shoot them down so low. They are so exquisitely sensitive to it. Yes, let's say last question. Yeah, right. That's a good question. So it's interesting to note, you probably already know this, that if you measure ketone use in a pregnant mammal, guess which one thing in her body is using more ketones than anything else? The baby is. The baby's using more ketones than any other tissue in her body at that moment. And so, of course, I'm not a clinician, so I can say whatever the hell I want, because I'm not like... It's the freedom of just being an academic. I've not seen any evidence that suggests a ketogenic diet is going to be pathogenic for a pregnancy. Of course, I want to be a little careful because pregnancy is such a complicated metabolic milieu, but I know of no evidence to suggest it's going to be overtly harmful. Indeed, I've known women who've done it and done it very well. They just gain a little less weight. But even still, if you were measuring their insulin sensitivity during the course of the pregnancy, it is worse. And it's supposed to happen, or it's better. It's supposed to happen. Okay, hey, thanks, guys. Thanks so much. This was great. Thank you.